Acceleration, the SI unit for which is meters per second per second. We usually say meters per second squared, right, like that, meters per second squared. The average acceleration of an object is the change in its velocity per unit time between two events. So average acceleration is always measured between two events, and it's the change in velocity, delta v, over the change in clock time, the time interval, delta t. And we write lowercase a for acceleration, a little av for average. You're probably most familiar with acceleration already when talking about automobiles, and you say things like, oh, this 1981 Honda Civic with these sweet flames coming off the wheel can go from 0 to 60 miles per hour in 15 seconds. That statement is a statement of the acceleration of that vehicle. 0 to 60 miles per hour. Okay, we're going to need to be converting miles per hour to meters per second pretty often. So you'll recall the conversion right there. Let's figure out the acceleration of this Honda Civic. Acceleration, the average acceleration, our definition is delta v over delta t. This is our initial velocity, 0, starts from rest, initial v, and the 60 miles per hour, that's our final velocity. That's the velocity at the end of the motion. So our delta v is the final velocity minus the initial velocity. After you convert 60 miles per hour to meters per second, you'll find it's about 27 meters per second. So final minus initial, which was 0 meters per second. And the change in time, it takes 15 seconds to do so, over 15.0 seconds. And that comes out to about 1.8 meters per second squared. Note, meters per second gives us meters per second squared. Another example, let's say we have a child on the monkey bars at the playground. The child drops from the bars, plummets towards the ground, and moves from 0 to 13.4 miles per hour in 0.61 seconds before striking the ground. Let's look at that acceleration. Again, the average acceleration between those two events, between releasing from the monkey bars and striking the ground, is the change in velocity between those two events divided by the change in time between those two events. Our final velocity minus initial, when you convert 13.4 miles per hour to meters per second, you'll find it's about 5.98 meters per second. Final minus an initial of 0 divided by our change in time, 0.61 seconds. And that's going to come out to be about 9.8 meters per second squared, a very significant value. .8 meters per second squared is the acceleration not just of a child falling off the monkey bars, but of any object in free fall. We also call it 1g for short. Commonly we call it an acceleration of 9.8 meters per second squared is 1g, g for gravity, because this is an object falling under gravity. For doing rough estimates, we can say a g is about 10 meters per second squared. All right, so this here is equivalent to 1g. Looking back at our Honda Civic, which accelerated at 1.8 meters per second squared, if we've got 10 meters per second squared in a g, we can say that that is about 0.18 g's. So pedal to the metal in your Honda, you're accelerating at about 0.18 g's, 0.18 times your acceleration if you were falling straight down. Try a couple of these on your own. Find the average acceleration in meters per second squared and estimate it in g's of a 2001 Ferrari 458 Italia, which can go 0 to 60 in 3 seconds. Of a Saturn V rocket, NASA's rocket that launched the Apollo capsules to the moon, which on liftoff will go from 0 to 5,150 miles per hour in about 161 seconds. And also of a bullet fired from a rifle. It accelerates from rest to 710 miles per hour when it exits the barrel. So from this speed to that speed, it's accelerating in the barrel. and it takes about 2.8 milliseconds to travel that far. You should know how to convert milliseconds to seconds. Look it up if you don't. Okay, pause the video for a moment, work out those average accelerations. Got the answer? Okay. Our Ferrari, about 8.9 meters per second squared, about 0.9 Gs. That Ferrari can accelerate almost as fast as you can fall straight down. Compare that to our Honda Civic, quite a significantly greater acceleration. Our Saturn V rocket, however, beats it. The Apollo astronauts experienced 1.4 Gs on liftoff, a greater acceleration than from falling. And a bullet, however, experiences about 11,000 Gs in the barrel of a rifle. If you experience that many Gs, you would be liquefied. Okay. Velocity has a direction to it, though. You can have a positive velocity or a negative velocity. So you can have a positive acceleration or a negative acceleration as well. So let's look at the difference there. Here we've got a motorcycle. It's 6 different moments in time, 6 different events. And we've got its velocity at each event and the time on a clock, starting from 0 seconds at event 1. So we see it first from event 1 to 2. It's going from 9 meters per second to 33 meters per second. It's speeding up. Then from 2 to 3, it's slowed down a bit. Then between event 3 and 4, it actually came to rest somewhere in between there and turned around and is now moving in the negative direction. So by event 4, its velocity is a negative 13 meters per second. And then it's speeding up in the negative x direction. So by here, its velocity is a negative 40 meters per second. And then it's slowed down some, but still is moving in the negative direction by the end, negative 13 meters per second by event 6. Let's look at the average acceleration between some of these pairs of events. Between 1 and 2, final velocity minus initial velocity, 33 minus 9, over the change in time, 4.8 minus 0, gives us 5 meters per second squared. Our velocities were positive, and he was speeding up the whole time, which gives us a positive average acceleration, positive 5 meters per second squared. Between events 2 and 3, final velocity 18 minus initial velocity 33, and final time minus initial time. Our calculation here gives us a negative 2 meters per second squared. His velocity was positive the whole time. He was moving in the positive x direction the whole time, but he was slowing down. His final velocity was less than his initial velocity. So the change in his velocity was negative. That means he has a negative average acceleration. Between events 4 and 5, he was moving slowly in the negative direction. Then by event 5 was moving very quickly in the negative x direction. So final velocity, negative 40, minus initial velocity, negative 13 meters per second, over final time minus initial time. Gives us a negative 6.9 meters per second squared. His velocity was negative the whole time, but he was speeding up. He was moving faster and faster in the negative x direction. That means he has a negative acceleration. He was moving faster in the negative x direction. His negative velocity was increasing. His velocity was getting more and more negative from this event to this event. Many ways to phrase that. It's a negative average acceleration. Lastly, between events 5 and 6, he was moving quickly in the negative direction, and then he slowed down but was still moving in the negative x direction by the end. Final velocity, negative 13, minus initial velocity, negative 40. Negative 13 minus negative 40. Be careful of these double negatives. Be sure that's going to be negative 13 plus 40 over final time minus initial time. Comes out to about 3.0 meters per second squared. Positive acceleration this time. His velocity was negative the whole time, moving negatively at event 5, moving the negative direction at event 6, but he was slowing down. His velocity was becoming less negative over that time interval. In other words, his velocity was becoming more positive, going from a large negative number to a smaller negative number. We call that a positive average acceleration. Note, no such term as deceleration in physics. We use that word in common language, but in physics, when discussing kinematics, we don't use the term deceleration. We have either negative acceleration or positive acceleration. That's what we can say. No decelerations. So when we're slowing down, like from event 2 to 3, that's not deceleration, that's a negative acceleration. He was slowing down, that's a negative acceleration. Likewise here from events 5 to 6, he was slowing down, but his velocity was becoming more positive. So that's a positive acceleration. No deceleration. Okay, when you work out a couple of these on your own, find the motorcycle's average acceleration between events 3 and 4, 1 and 3, and 4 and 6. Pause the video, work that out. Here's the answer. From events 3 to 4, he was moving in the positive x direction, positive velocity. Then by event 4, he was moving in the negative x direction, negative velocity. So his velocity changed directions. Final minus initial, negative 13 minus 18, is a negative change. So that's a negative acceleration. His velocity switched directions. If it switched from positive to negative, that's definitely a negative acceleration. Between events 1 to 3, final minus initial is a positive acceleration. Now note, he was moving faster at event 2 than 3. He was slowing down by this point, but still at event 3 he was moving faster than he was at event 1. So that's a positive acceleration, final minus initial. And then from events 4 to 6, his speed here is negative 13. At event 4 was negative 13. So his velocities were the same at those two events. It was different in between. He sped up in between those two events, but he ended at the same velocity where he started. If you end at the velocity where you start, the change in your velocity is 0, so you have a 0 average acceleration. One more example for you to work out. More conceptual here, no numbers. Okay, this picture represents a scene at one moment in time. This is a freeze frame of one event. Then here on the right, we have a freeze frame of a second event. We have an alligator, a log, a turtle, a truck, and a race car. And the arrow indicates the velocity of each object. So a short arrow indicates a small velocity, large arrow indicates a large velocity. So for instance, at time 1, our gator has a small negative velocity, our log has a large positive velocity, our turtle has a small negative velocity, truck has a large negative velocity, and the race car has a small positive velocity. And you can see how each of those has changed by time 2. What I want you to do is tell me which of these 4 objects, there's 5 of them, which of these 5 objects has a positive average acceleration from time 1 to time 2, and which of these 5 objects has a negative average acceleration from time 1 to time 2. Pause the video, think about that one for a moment. Got the result?